Welcome to Exploring Computing. Today's video is Bits, Bytes, and Binary, Part 4, in which we learn how to represent Egyptian hieroglyphs on a computer. So far we've concentrated on how to represent numbers on a computer. But many of you listening to this video are probably people who spend more time typing and writing than you do calculating. So I'd like to switch gears here and talk a little bit about how we can represent text on a computer. We talked briefly a couple videos ago about how different combinations of bits might be used to represent different things, like the state or province that somebody might live in, or the dorm that somebody might live in. And so a natural way of thinking about this is we can represent text by using different character combinations. And by the way, if you hear some whining in the background, that is my dog Maddie. She's all psyched and excited and wants to know why I'm not playing with her. Anyway, what I'm going to show you next is something called the ASCII table. This is the ASCII table. You can see that what we're seeing here is that different combinations of bits can be used to represent different specific letters or numbers or even punctuation on the computer. Let's take a close look and see how this is done. So in the upper right-hand corner of the ASCII table, we can see here we have the representations for A, B, C, D, E, and F, both upper and lowercase. Suppose the computer were to see the bit combination 10000001 or on, off, 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 on. We can see that this would actually be representing the capital letter A. In contrast, if it were to see this particular bit sequence, 1100101, or on, off, on, it actually represents the lowercase letter E. Now, I should caution you that these particular interpretations of these bit patterns is only true for computer programs which are designed to work with text. Remember, a particular sequence of bits can represent different things depending on what the particular program that's looking at these bits is designed to work with. Let's take a closer look at our original bit pattern for the letter A, 10000001. As we've seen, if we're working with a program that works with text, such as a word processor, this will be interpreted as the letter A. However, if we're working with a different program, say a program that's designed to work with numbers, this could actually be interpreted as the number 65. Why? Well, let's take a quick look at the math here. So we've got our 8 bits here. Starting on the right, our 0 bit, this represents 2 to the 0 power, which is 1. And then next to that, we have our 2 to the first power, which is 2, or 2 to the second, which is 4, or 2 to the third, which is 8. We've got 16, 32, and 64. So if we look at this, we have 1, 2 to the 0th power, which is 1, and 1, 2 to the 6th power, which is 64, and so we have a total of 65. I think it is important when we're looking at these bits to remember that at one level, as far as the computer is concerned, bits are just bits. The thing that determines how those bits are interpreted is the program that is working with them. As long as a program that is working with these particular bits is thinking of them as ASCII, then what it will be interpreted as is the letter A. There are other possible interpretations. It could be a number, it could be a sound, it could be part of a picture. But in this particular case, we're going to assume that our program knows that this is an ASCII character. And so it looks it up in the ASCII table and displays it as an A. Let's take another look at the ASCII table here. I want to focus on the left-hand column now. Now, if you look at the left-hand column, you'll notice that the left-hand column actually has punctuation marks and the numbers 0 through 9 when they're represented as part of a text document. Now, if we focus on the upper left corner here of this table, you'll notice something a little bit odd about the numbers here. If you look carefully, you'll notice that our upper left-hand column does not start off with the number 0. Instead, you can see that it starts off with a 0, 1, 0, 0, 0, 0, 0. This will be even more obvious if we go ahead and switch this to decimal. You can see here that the codes representing the ASCII characters start off with the number 32 and go up to 127. Why does it start off with 32? What happens below the number 32? Well, it turns out that there's a whole another set of codes going from 0 to 31, which represent what are called the control codes. If you look at the corner of a keyboard, particularly a Windows keyboard or a Unix keyboard, you'll see that there's a control key. And by holding down that control key and typing different characters, we create different control characters. This next table here shows you some of the more interesting control characters. So you can see that, for example, the control H character represents the backspace. The control M represents the carriage return. And you can see that some of these were originally used for back in the day when we had teletype, which was basically a typewriter that was connected to the computer. And in this particular case, the control G, which I've always been rather fond of, would actually ring a bell. And for quite some time, if you were working in a text editor and you hit the control G, your computer would actually ring a bell. It was actually kind of cool, but I'm afraid I haven't run into any text editors lately that do that. But the basic idea here is these different control characters allow us to transmit control information using the same ASCII character set. One of the odder aspects of the control characters that you will sometimes run into is that the computer manufacturers did not agree on what the correct character to use for the end of a line was. Unix computers, Microsoft Windows, and pre-OS X Macintoshes all use different characters to indicate the end of line. The main two characters involved here are Control M, which stands for carriage return, and Control J, which is line feed. Historically, the Control J line feed would take the piece of paper currently in the teletype, and it would shift up that teletype by one line. And then the Control M would return the printing cartridge from wherever it was currently on the line and return it back to the start of the line. Microsoft Windows assumes that you need to perform both operations. You need to perform a Control J operation to shift down to the next line, and you need to perform a Control M to move to the start of the current line. Unix just uses the line feed. It just uses a Control J, and pre-OS X Macintosh just used the carriage return with a Control M. This can lead to odd situations. So I've seen editors where a standard text file written on one operating system, you open it on a different operating system and it looks like garbage. So let's take a look at how this might work. On the top here, we have a text file that's been created on the Macintosh. And when viewed on the Macintosh, we've got the line Stanford University followed by the Control M, which is the pre-OS X Macintosh version of the end of line, followed by computer science. And on the bottom here, what we see is how this might appear on a PC text editor. So what we've got the Stanford University as before, and then we've got the Control M, which is a carriage return. And on the PC, that just returns to the beginning of the line. It does not shift down a line. And so what we actually have here is that we have Stanford University and immediately on top of it, computer science. Fortunately, most modern editors are conversant enough in the various possible ways of ending a line that they will do the translation for us. That said, most high-end text editors, particularly those designed for programmers, will allow us to set which convention we want to use. So this image here shows the settings for Sublime in the top left, Notepad++ on the right, and Visual Studio Code on the bottom. And you can see these all have options for deciding whether we want to use the Unix convention, the Windows PC conventions, and in some cases, the pre-OS X Macintosh conventions. Another place where this distinction between how we're going to represent the end of line for these different operating systems shows up is when we're using file transfer programs. Now, file transfer programs distinguish between text files and binary. And so one of the questions is, why do we have this distinction? And so what we're seeing here is this is secure FTP. This is a program that Stanford recommends for transferring files for Windows computers to, say, the Stanford Unix machines. And you can see that Secure FX is asking me if I want to treat a particular file as a text file or a binary file. Well, why does it need to know the difference between these two? Don't we just transfer each of the individual bits and bytes over and then our file transfer is done? Well, what it's actually asking here is it's saying if this is a text file, it is going to go through the text file and look for each of these end of line sequences, and it's going to convert from whatever it sees in the file. For example, if it's going to say, oh, I see that you're using the Windows convention, or I see that you're using the Macintosh convention, and it's going to look at the computer I'm transferring it to and say, oh, you're transferring to a Unix computer. So what I'm going to do is I'm going to take the convention that's being used by the computer that you're transferring from, and I'm going to convert those end-of-line characters to the proper sequence for the computer that you are transferring to. Let's go back to that ASCII table. If you look carefully at the ASCII table, you may realize a couple things. The first thing that you may notice is that there are only 7 bits for each of our characters. And as you know, computers generally work with sets of 8 bits or a byte. And so that actually means there's a whole bunch of combinations there that we're not taking advantage of. We're only taking advantage of 2 to the 7th possible combinations, or 128 combinations, when if we have a full byte, we actually have 256 combinations. The other thing you may realize is that this is a very English-centric table here. You know, even looking just at Europe, there's a whole bunch of different characters we need for European languages that aren't listed there. And obviously, there are a whole bunch of other languages that aren't European, and they don't have characters listed at all. And so how are we going to handle this? Well, one of the things that we can do is we can take advantage of the fact that we do have 256 combinations in a byte. We can say, oh, 128 of those are set aside for the English characters, and the remaining 128 we can use for different purposes. And so this is what a standard called ISO 8859 does. There's a number of related ISO 8859 standards. So you can see here I've got a list where ISO 88591 represents Western European characters. You see I've got some samples there. 2 is Central European, 3 is South European, and so on. We've got Arabic, we've got Greek, we've got Hebrew, and there are a whole bunch of these other sets. And these all work with languages where we can fit all the letters needed for the language in 256 characters. The way this particular standard works is, 1, we have to tell the computer program which one of these character sets are we using. Are we using the Arabic character set? Are we using the Hebrew character set? Are we using the Cyrillic character set? Which one of these are we using? The next thing we need to do is we need to look at our 8 bits here. And you can see I've got 7 of the lower end bits are 110, 1010. And then if the high end bit is a 0, that means I'm using the standard ASCII table, and this would actually be a J. If the high end character is a 1, that means I'm using ISO 8859. And then the particular character it would represent would depend on whether I'm using ISO 88591, 2, 3, and so on. And so here are some of the possible interpretations of what this particular bit sequence means based on the particular ISO character set I'm using. Now, we do need to have the ISO character set correctly. So what I've got here is I've got a web page I've written in French, and you can see as I change the character set being used, for example, if I don't correctly tell the web browser which character set to use, and it thinks that, oh, this is Cyrillic, or this is Arab, or this is Greek, you can see that the web page is going to appear differently and incorrectly. Now, what about non-Western languages? Well, there are a number of different standards for these as well, and most of these use 16 bits. So in 16 bits, we can represent 2 to the 16 different characters, which you'll recall is 65,536. And that's going to be enough to represent most of the characters in, say, for example, Chinese, although there are probably going to be some ancient and not very frequently used characters that aren't going to fit in our 65,536. So these are going to be used for different languages that don't fit in 2 to the 8th combinations. And again, we need to have a program that understands them. We need the program to understand the particular character that's being used. This is a copy of Harry Potter and the Philosopher's Stone that I got from the Pottermore website. I was learning Japanese, and on the far right, we can see that these are the names of the chapters in Japanese. And what we have on the left is, well, we basically got garbage. What happened here is that when I got the files from Pottermore, I downloaded them to my PC, which was expecting characters that were only 8 bits long, and the characters used by the Pottermore files were 16 bits, and my computer did not know what to do with them, so it basically turned the names of the files into garbage. So the problem we're seeing here is that different bit combinations represent different things depending upon the particular encoding. So we can have one character combination that represents an E in English, and the same character combination might represent tsu in Japanese. So what we need is a more unified system, and it turns out there actually is a more unified system. Unicode uses between 1 and 4 bytes per character, and if you do the math, 2 to the 32 possible combinations, because there are 32 different bits in 4 bytes, allows for 4,294,967,296 combinations. So that's a heck of a lot of combinations. And not only does Unicode allows to store all the different languages that we've already seen, it also has bit combinations which will allow us to represent ancient languages like Egyptian hieroglyphs, Sumerian cuneiform, and even Mycenaean Linear B, which we have seen, but we don't actually know how to read. It also includes things like musical characters and emoji. So what we're going to do is we're going to take a quick look at how you might use this Unicode in, for example, a history document. So let's say I'm writing a history paper and I need to use Egyptian hieroglyphs in my history paper. The first thing I need to do is I need to get a hold of a font that can display Egyptian hieroglyphs. So remember, Unicode only specifies the particular bit sequences to represent these, and it guarantees that there's a unique bit sequence that for my Egyptian hieroglyphs that can't be confused with, say, Chinese characters or Korean Hangul or English letters. So every single one of these different marks that human beings make in order to represent language has a unique bit combination, and they can't be confused one for the other. That being said, that doesn't mean that every font has every possible one of these 4 billion combinations worked out so it knows how to draw it. So, for example, if you use Times New Roman is designed for English and European languages. It is not designed to show Mycenaean Linear B. So, if we were to see that bit combination for a Mycenaean Linear B character in Times New Roman would be like, I don't know what that is, so I'm just going to draw a block. So you will often see either blocks or little diamonds with question marks in them. These are different indications that the font that you are using understands that there's this unique bit pattern, but it does not actually have the ability to display that unique bit pattern. So the first thing we need to do if we want to write our paper with Egyptian hieroglyphs here is we need to go ahead and find a font that supports Egyptian hieroglyphs. So, you can just go to Google Egyptian hieroglyphs Unicode font, and you will get a bunch of different hits. I chose one that was supported by the open font license, so I could go ahead and use it for our class. There are many, many more choices if you're just using it for personal use. And it turns out Google actually has a bunch of fonts for things like Egyptian hieroglyphs or Sumerian cuneiform or Mycenaean Linear B. And so those are actually the ones that I'm using here for this lecture. Okay, so we need to go ahead and download that font and we need to install it on our computer. And the process for that is going to vary depending on the type of computer you have. The next thing we're going to do is we're going to find out what the particular bit pattern that we want to use for the particular character we want to reproduce in our paper. So we can look up a table. It turns out Wikipedia has tables for many of the different languages supported by Unicode. So here's the table here on Wikipedia for Egyptian hieroglyphs Unicode. And what I'm going to do here is I'm going to look at the column on the left, and I'm going to look at the rows on the left, and I'm going to look at the columns on the top, and I'm going to combine those two in order to form a unique number. Now, these are actually in hexadecimal. This is a numbering system that's very closely related to binary. You can think of it as a very compact form of binary. We'll take a closer look at this in more detail another week. I think, one numbering system for the week is enough. So we're just going to stick to our binary for this week. But another week, we'll take a close look at hexadecimal, but these are hexadecimal here. So I'm going to figure out what the hexadecimal number is from this table. Then I'm going to go ahead and go to Microsoft Word. I'm going to set the font because, again, remember, if I use one of the standard fonts like Arial or Helvetica, they don't actually have drawings for Egyptian characters in them. So I need to switch to my font that has Egyptian characters in it. And then I'm going to insert symbol. This is how Microsoft Word will allow you to insert any Unicode character. So switch to the insert tab, and on the far right, there's insert symbol, and go ahead and click all the way down to the bottom where it says more symbols. And that will go ahead and bring up a dialog box. And I'm going to go ahead and enter in that Unicode code from the table on Wikipedia. I'm going to go ahead and enter that into the dialog box. And then that's just going to go ahead and insert my Egyptian character there in my document. So there you go. I'm all set. I now know how to enter Egyptian hieroglyphs on the computer. So now that we've taken a look at how the computer represents some basic data types, In the next couple lectures, we're going to turn to some more complex types of data. We're going to start off by taking a look at how computers represent images. This lecture is going to be useful if you're planning to shop for a new computer or a new television. We'll discuss the underlying technology and the terminology. And it's also going to be very useful if you're planning to create any sort of digital imagery and you need to know what the correct tools and what the proper formats to store your files in are. After that, we're going to take a look at how computers represent music and sound. And between the digital images and the sound lecture, we're going to take a closer look at the critical difference and a critical understanding of the difference between digital and analog. I look forward to talking with you all again soon.